Okay, in this example, we have block B. Block B is constrained to be moving along the smooth vertical guide. There's a force, a 50 Newton force, which is applied to B at this angle of 30 degrees from the guide. There's a spring which is attached to block B, and the other end is fixed to ground. And the system starts out from rest. What we want to find is the speed of B when it's reached a height of, looks like 1.5 meters above where it began. The spring begins horizontal, and it has an unstretched length of 1.5 meters. All these details will become more important to us when we write down our energy expressions. Okay, we know the first step. We need to figure out what, if any, forces do non-conservative work. That's the purpose of our FBD here for the work energy equation. What forces do we have? Well, we've got the applied force F. It's a constant magnitude, constant direction force. We have a spring force, like this. We have a normal force. Not really sure on which side it acts, but the good thing about it, it's not important because it doesn't, as we'll see, it doesn't do any work. And then, of course, we have the weight force. We go through the process of finding out what does work. N, normal to the path, can't do any work. mg does work, but we're going to put that in V. Spring force does work, but we're going to put that in V. So the only thing that we have doing work is F. As F moves along, it's always going to be at this fixed angle with respect to the tangent vector of point B. So this angle is always 30 degrees. We'll use that when we get ready to calculate the work. Okay, so for the work energy equation, T1 starts out from rest. V1. Well, we have two parts. We're going to have a potential due to gravitational force, potential due to the spring force. For the gravitational, I'm going to choose my datum line where block B starts out. So there's no potential due to the gravitational force. There will be a potential due to the spring because the spring is actually stretched at that point. The plus is there because that's always there. It's always a plus. No minus signs here. Whether it's stretched or compressed, it's always a plus. T2. 1/2 mv squared. V2. V2 is going to be an mgh2. There's a plus sign because it's going to be above the datum line. And there's a plus in front of the spring potential 1/2 k delta squared because it's always a plus. And we now need to find the work. So the work is all done by F. So if I take F as a vector, I dot it with the unit vector over which B moves, and then integrate it over the path of B. I know that this number here is going to be a plus F cosine. A plus because the cosine projection onto the path is always pointing the same way as the motion. And since F and the angle are constants, we can bring that on the outside. So the work is just going to be F cosine theta times the distance delta S through which B moves. Okay. Therefore, our work energy equation, T1 plus V1 plus the work is equal to T2 plus V2. Starts out from rest. V1 just was a 1/2 K delta 1 squared. The work term, F times cosine theta, that's a constant. And delta S in this case is just going to be the same thing as H, the H2 that we had for V2. So that's the work term. 1/2 mv squared starts out the right hand side, and V2 we saw was equal to mgh2 plus 1/2 K delta 2 squared. So it looks like a very straightforward equation, which it is, but we still need to do a little bit of work here, because we need to explicitly write down what the stretch is in the spring at the beginning. F we know, theta we know, H2 we know, V we want to find, and we also need to be able to write down an expression for delta 2. So that's going to be where our kinematics comes in. Well, delta 1, which is equal to the amount of stretch in the spring at the beginning, the length of the spring, is 2. But it said that the unstretched length was 1.5. So that's like L1 minus the unstretched length. So L1 in this case is 2, unstretched length of 1.5, so that's a 0.5. Delta 2. It's going to be the total length of the spring at position 2 minus the unstretched length, L2 in the end. So let me just draw the right triangle here. This is where the spring's attached to ground O. This is B at position 2. This distance is equal to 2, and this distance is 1.5. So L2 is going to be the square root of 1.5 squared plus 2 squared. This is L2. The unstretched length, again, was given to us as being 1.5. That's given information. So we have delta 2 and delta 1. So with that information, and just reminding ourselves here that H2 is equal to 1.5, we can solve for V, and V is going to be equal to 2 over m times the quantity here of 1/2 K delta 1 squared minus delta 2 squared, like that. We're going to have an F cosine theta, subtract away an mg times h2, like that, and we take a square root. And that's it. We worked the problem in the standard way. We looked first to find out what forces are doing work. Only F does work. We wrote down T and V. There's no potential at the beginning because I chose my datum line to be the initial state. There is an initial stretch in the spring, so we have to put in 1/2 K delta squared. T2 is the usual 1/2 mv squared. V2 will have a change in height, mgh2, contribution to potential. There is, of course, going to be a stretch in the spring at position 2, so we have that summed together. And the work done by F, that's plus, because its component along the path, F cosine, is always pointing the same way as the motion, and so that's how we got the plus sign in front of this expression for U. We put everything together. And lastly, take great care here on finding delta 1 and delta 2. Delta 1, initially the spring was stretched a length of 2. It had an unstretched length of 1.5. We did a little bit of trig to find the length of the spring at position 2. Subtract away the unstretched length, 1.5. Substitute those all in and solve for the speed V.